All right, today we're going to talk about learning about extrema on interval part 2. So earlier you guys did part 1 of this where you were learning about critical numbers and you were learning about relative extrema. So relative extrema, like we talked about earlier, is any point that is either a max or a min, and any point that isn't necessarily the global max or the global min, so the absolute epitome of it, but anything that's like in between. So today we're going to talk about absolute extrema, so talking about like the highest or the lowest, not just a high point or a low point. So here we go. The definition of extrema. So extrema sounds extreme because they're the outermost point. So it's either the very highest of the high points or the very lowest of the low points. It's not just a low point or a high point, it's the highest point or the lowest point. So it says extrema. Let f be defined on an interval I containing some point c. F of c is the maximum on f of f on I. If f of c, let me write this in purple. If f of c is greater than or equal to f of x for all x in a to b. And that's the closed interval from a to b. And vice versa, f of c is the minimum on f of f on I if f of c is less than or equal to f of x for all x in a to b, the closed interval. So essentially what that's saying is a point is the very highest point. A point is the maximum. F of c is the maximum. If it's greater, if when you plug it into the function, when you plug c into the function, if that value for y is greater than all the other values around it in that interval, then it's the maximum. And vice versa. A point c is the minimum, or it's the value of where the minimum occurs, as long as it is the y value when you plug it into the function, as long as the y value is the smallest y value on that entire interval that you're looking at. So it says the minimum and maximum on the interval are called extreme values. Extreme values. Or in other words, we call them extrema. And again, the reason being is because they are the highest or the lowest points on the graph. Absolute extrema, all right, so here's what we're talking about today. Absolute extrema occur at the highest y value or the lowest y value. All right, so the very top of the top or the very low of the low. And we're actually going to be looking on intervals today, so as long as it tells you that it's on an interval, you have to look at the endpoints as well, and we'll talk about that. So relative extrema, so this is what we're talking about today, these absolute extrema. What we talked about in the notes before this, previously in the first section of these notes, was we talked about relative extrema. So absolute extrema is the highest point or the lowest point, whereas relative extrema occurs at a high. So it's not the highest point, but it's one of the high points. So let's say a graph is going up and then it turns down and then it's going up again and it turns down. So you might have multiple high points and multiple low points, but the absolute extrema is the highest and relative extrema is just one of the highs and one of the lows for minimum. So let's look at some pictures. There's not much room in your notes to write this, but squeeze it in somewhere. If I draw this picture, notice that it has arrows on the end. So it goes down forever and it goes up forever. So this graph does not have any absolute extrema because it doesn't have a lowest point and it doesn't have a highest point because it goes to infinity forever up and it goes to infinity forever down. However, it does have a relative max. This is a relative max. I'm just going to abbreviate relative max. And this point down here is a relative minimum, so a relative min. Now again, they're not the absolute max and they're not the absolute min, but they are relative because it is a high point on the graph and it is a low point on the graph since it's turning. If it was a absolute min or max, you'll see how we write that a little bit differently right now. So let's say we drew something like this. All right, again, this graph does not have any minimums, no absolute minimums, okay, because it goes down forever. However, it does have an absolute maximum. This is the very highest point on the graph. We just call that max. So if it just says max, that means it's the absolute max. That's the highest point on the graph. All right, this one is a relative max. I always have to include that word relative before it if it's not the highest point. And this point down here is a relative minimum. All right, so on this next slide, the extreme value theorem is what we're going to look at next. It says if f is continuous on the closed interval from a to b. So here's where we start looking about where it has endpoints. So now it's not an infinite graph. Now they're going to give you a start and an endpoint. So that does affect our mins and our maxes because your endpoints are actually allowed to be mins and maxes in this case. So if f is continuous on the closed interval from a to b, then f has both a minimum and a maximum. So it isn't an infinite graph like I just said, so it has to have a minimum and it has to have a maximum. And by those I mean absolute minimums and absolute maximums. So let's make ourselves a little note. Those maxes and mins can occur at the critical points. Actually, I'm just going to start abbreviating critical points as CN for critical numbers. Or they can occur at endpoints. All right, so make sure that you test both all the critical points and all of the endpoints for what is the absolute minimum and absolute maximum. So let's look at 4 different cases. I'm actually going to add in one more graph over here. All right, so the first case we're going to look at is on the closed interval from 1 to 5. Oops. So closed interval means it includes this point and then it includes this point. So here's our point C, here's f of C. All right, this is our absolute maximum, so I'm just going to write max for absolute max. This one down here is our absolute minimum, so I'm just going to write min for absolute min because it is the lowest point on the graph. There are no arrows, so it is one of the endpoints that happens to be the lowest point on the graph because it stops at 1 and it stops at 5. This one over here, this one is neither a max nor a min, however, it is a relative min. We don't care so much about that, but it is good to know that it is a relative min. It's the lowest point in a small neighborhood, but it's not the lowest point on the entire graph. If we look at the second one, let's look at an open interval from 1 to 5. So now we do not include these 2 points, so these are open circles. So here's C, and here's f of C. So our maximum is still up here, so this is still a max. However, our 2 endpoints now, because it does not include those, you can always find a point that gets closer and closer and closer to that point that's just lower and lower and lower, but you will never reach that point. So there is no lowest point on the graph because there are infinitely many values that get closer and closer and closer to that point. So because we do not include that point, that means there is no min. For this one, we're going to look on the open interval again from 1 to 5. Oops, open interval. But this one we're going to look at where C is actually an open hole. And remember, if you read back up above at the extreme value theorem again, it says if f is continuous on the closed interval. And because here we made it so that it was not continuous, that's why there's an issue here. So there's no max or min on this one. So there's no max or min because it's not continuous on the closed interval. And that's why the second one gave us a problem as well. So this one was not continuous. The one we just drew was not continuous. And then this last one as well. Let's say I do it on the half open, half closed interval. So if it's open at 1 but closed at 5, it does have a max up here. All right. And it does not have a minimum again because even though this point here is defined, because this one over here is not defined and this one is lower than the first one, that means that there is no minimum. So no min. All right, good. Let's move on. We have one more little page of notes and then we'll get to some examples. All right, so in order to find the extrema on a closed interval, here's what we do. It says find the critical numbers by finding the derivative and setting it equal to 0. Just like we did earlier, to find the critical numbers, we find them by setting it equal to 0. We also need to determine any values where the function is undefined, so where f prime, is undefined. So this is the new part. In order to find the extrema, you have to evaluate f at each critical number and evaluate f at each endpoint. So all that means is that when you get your x values, plug them back into the function for the endpoints as well as for the critical numbers to figure out what the y value would equal at that x value. It says the least of these values, so I'll go ahead and highlight that, the least of these values is the minimum, so the smallest y value is the minimum, and the greatest y value is the absolute maximum. So we're going to go ahead and practice a few of these examples. Now, I want to actually skip over the first one because we're going to come back to trigonometry later. Let's look at the second one. So it says determine the absolute extrema of g of t. So if you look back over at the front again, first step, it says find the critical numbers by finding the derivative and setting it equal to 0. So let's find the derivative of this. G prime of t. All right, these are two things being divided, so we have to use the quotient rule. So we do the derivative of the top, so the derivative of t squared is 2t, times the bottom, so times t squared plus 3, minus the top, so t squared, times the derivative of the bottom, so 2t. All over the bottom squared, t squared plus 3 squared. So let's simplify this a little bit. If I distribute in the top, I get 2t cubed plus 6t. And then I distribute the t squared, I get negative 2t cubed. All over t squared plus 3 squared. Simplify one more time up at the top. The 2t cubes cancel, so I get 6t over t squared plus 3 squared. All right, so we found the derivative. The second part of that first step over there again on the first page says set it equal to 0. So I know that fractions will only equal 0, so this is my fraction over here. I know that this is only going to equal 0 when the top equals 0. So I know that g prime of t will equal 0 when 6t equals 0. So therefore t equals 0 is one of our critical numbers. Okay, so I'm just going to put a little box around that to hold our place. That's a critical number. Step 2. Step 2 says determine if there are any values where f prime is undefined. So in order to figure out where a fraction is undefined, we need to know where the bottom equals 0. So if I set g prime of t and I want to know where it's undefined, I will set the bottom equal to 0. So I'll say t squared plus 3 squared equals 0. Take the square root of both sides, so I get t squared plus 3 equals 0. Subtract 3 from both sides, so I get t squared equals negative 3. And if I take the square root of both sides, I get t equals plus or minus the square root of 3i. And because that's an imaginary number, that means that this one is not going to work, so we really don't care about those solutions because our function is never undefined. So we only care about our critical number of t equals 0. All right, so we have one critical number. Next, we did step 1. We found the critical numbers by finding the derivative and setting it equal to 0 and determining where f prime was undefined. Step 3, it says evaluate f at each critical number. All right, so here's what it means to evaluate f at each critical number. It means take the critical number, which is 0. By the way, don't forget this. I'm sorry, I forgot to tell you earlier. Make sure that you always check your critical numbers in the original equation. All right, so check your critical number in the original equation just by plugging it in your head really quick. Check it to make sure that when you plug it back in, it does not make that original equation undefined. So if I plug in 0, I get 0 over 3, and that's fine because that is not undefined. So I checked it just to make sure I did it right. All right, let's come back over here. So I'm evaluating t equals 0 in this function g. So if I plug in 0, I get 0 squared over 0 squared plus 3, which is 0. So that was step 3. Step 4 says evaluate f at each endpoint. So I'm going to evaluate it at the endpoints. And here are my endpoints up here. So g of -1 equals -1 squared over -1 squared plus 3. So that's 1 over 1 plus 3, or in other words, 1 over 4. So 1/4. And my other endpoint is 1. So g of 1 equals 1 squared over 1 squared plus 3, or in other words, 1/4. So let's look at this. I evaluated my critical number and I got 0. I evaluated my endpoints and I got 1/4 for both of them. The last step, step 5, says the least of these values. So the least would be the smallest value. So the smallest value that I see up here is 0. All right. The least of these values is the minimum. So that means that this point is the minimum. The greatest of these values, so I see these two are actually equal to each other, so they must be the greatest. The greatest of these values is the maximum. So when I write it, and I guess I don't have much room to write it, so I'm going to do some erasing. Let me erase this over here. When I write it, I write max, and then I put the point, which is the maximum, and I found that the maximum was at 0, 0. I'm sorry, that's the minimum. I found that the maximum was at 1, 1/4, and there's another one at -1, 1/4. And for the minimum, I found that my minimum was at 0, 0. So we did everything that problem asked us to do. It says determine the absolute extrema. So these are the absolute extrema on the interval. We have 2 absolute maximums and 1 absolute minimum. All right, let's try number 3. We're actually going to hold off on number 3. We will finish this one later. So go ahead and bring your notes to class with you on Monday, and we will finish these on Monday. But still work on that homework for tomorrow in class.